So a quick radiation primer to give you the context of why in the climate we call those the short and the long wave radiation. You keep in mind that all objects emit radiation according to something called the Planck function, which the physicists among you would be familiar with. It's written here as this B of nu and T, where nu is actually the wave number and T is the temperature. But the key point here is that higher temperature objects emit at shorter wavelengths and higher frequencies. And so if you think about radiation from the sun is really hot, which means it emits at really short wavelengths. So that is the red part of this spectrum you can see here is all the shortwave radiation, which is coming from an object at about 5,000 Kelvin, which is the sun. Now, of course, the atmosphere and everything on Earth is much, much cooler than that. And so it emits at much longer wavelengths and lower frequencies, out here at around 200 to 300 Kelvin in this pink part of the spectrum. So of course, these things are on a continuum. They're all just electromagnetic radiation. But because in the climate system, we have these two very distinct regions, one from the sun that has very, very short wavelengths and one from the terrestrial sphere, which has very long wavelengths, we just split them into two boxes and call them the short wave and the long wave. The other thing to keep in mind is that in this course, we don't really deal with the details of the wave number dependence, so this Planck function. Instead, we're only ever interested in the total radiation. So if you integrate the total emissions, so that's the area under these curves, you find that that is this sigma t to the 4, where sigma is this thing called the Stefan-Boltzmann constant. So that sigma t to the 4 is the long wave radiation from the sea surface if you use the sea surface temperature. It's a little more complicated for the radiation coming down from the atmosphere because that comes from many, many different levels in the atmosphere.